Well, welcome. Thanks for coming. Thank you. We have a couple of remote locations watching as well, Leeds and Edinburgh, and welcome to Leeds and Edinburgh as well. My name is James Weaver, and I'll be talking about Spring and Reactive. And the title of the talk is Reactive Card Magic, which you'll come to understand why I'm calling it that. But it's about the web on a reactive stack with Spring. There's my coordinates. Please reach out to me anytime. My email, my Twitter, and I have a couple of blogs. One's a technical blog at javafexpert.com, and the other one is a musical blog, kind of a technology and music blog that is culturedear.com. And a little bit about me. I'm a developer advocate with Pivotal. I travel all over the world and speak about technologies, different kinds of technologies, machine learning, quantum computing, Spring, Reactive, and I've written several books, mostly on Java and Java EE, Java FX, and most recently one on Raspberry Pi and Java. So I work for Pivotal, and our mission is to transform how the world builds software. And you may have heard of different products that we have. One is, of course, Spring. We're the stewards of Spring, Java Spring. We also have our brand of Cloud Foundry called Pivotal Cloud Foundry, and we're kind of the major contributor, committer to the Cloud Foundry project. We also have Pivotal Labs. There's one here in London where we team up with customers, get them used to agile processes, customer engagement. And the new kid on the block is PKS. That's production grade Kubernetes. And so we have some great technologies, but the thing that I like most working for Pivotal is our principles and practices. And here are three of them: do the right thing, do what works, and my favorite is be kind. And you don't have to ask me to be to be kind. I feel like I'm a pretty kind person already, but it's very refreshing to work for a company that one of their prime directives is to be kind. And God knows that in the world today, we need to be kind to each other, treating each other like we want to be treated. So what are we going to cover today? The title is Reactive Card Magic. What are we going to cover? Well, we're going to cover all things reactive in the new stack for Spring in Spring Framework 5. We're going to talk about Spring WebFlux, what it is, why it was created. We're going to talk about reactive systems and reactive programming and what the difference is between those two. Now we're going to discuss reactive programming in Java. By the way, how many Java developers do we have here? Okay, just about everybody. Wonderful. And Spring developers, people that have done Spring. Nice. Okay. And we're going to talk about then one of the reactive projects called Project Reactor. And then we're going to talk about the web client, which is a reactive client. And then we'll discuss code and concepts as we walk through code and concepts that are in this demo application that I've created for this session called Reactive Card Magic. So what is Spring WebFlux? And there's some buzzwords in here, and I'll be defining these as we discuss them. But it's a non-blocking reactive web framework that supports something called back pressure. And it runs on servers like Netty, Undertow, and then any Servlet 3.1 or later container. So non-blocking, you're probably all familiar with what non-blocking is. If I block, then that means I made a synchronous call and I'm waiting for the response. Non-blocking would be, I've made a request, but I'm not going to wait for the response. It's going to come later in the future. And reactive, I'll be discussing more what reactive is. Back pressure is this idea where I can control the flow. I can apply flow control to the response in case the response comes so quickly or I get so much data that I need to say, hey, slow down a little bit. So, in the old days, we used to call that flow control. Does anybody remember some of the protocols for flow control? Like X on, X off. Anybody heard of X on, X off? Or ENC-AC? Those kinds of things. I'm going way back. But that's the idea of being able to control the flow. And so, we have Spring with Reactive. That's the Project Reactor logo with Spring. And we have this thing called WebFlux that's like WebMVC. WebMVC is the model view controller framework for a web framework. But WebFlux is the reactive version of that. And so it turns out that it's very similar and easy to go from one to the other. So why was Spring WebFlux created? Well, one reason is because the proliferation of mobile devices, everybody, of course, is carrying a mobile phone, and then Internet of Things. And also, we're all living online now. And so it's not rare to have an application that has millions of clients. I'm here at Sky, you know what I'm talking about. And so, in addition, many like shopping apps or ones that can have wild fluctuations can have something called the Black Friday effect, which is, and in the U.S. it's the day after Thanksgiving. And that's the biggest shopping day of the year, and you can get denial of service attacks, essentially denial of service attacks when so many people hit your website. And so that's another reason for reactive. And so because of those kinds of factors, we need a non-blocking web stack. With a blocking web stack, what happens is every request requires a thread on the server, and if you're waiting, then if you're blocking, then that thread is dedicated to that request. If you get millions of requests, you need millions of threads. With non-blocking, then that's not the case. So we need a non-blocking web stack that handles concurrency, handles a massive number of requests at the same time with a small number of threads. Threads are expensive, both computationally and as well as cloud costs. And we want to be able to scale with less hardware resources. We want to be able to handle millions of clients with a smaller number of hardware resources than would normally be required. By the way, when I was looking at Black Friday, Black Friday in the US means day after Thanksgiving, and I was kind of doing a check for Black Friday here, and I saw on Wikipedia that Black Friday is like the Friday before Christmas. It's kind of a party day. Is that true, or is that just Wikipedia nonsense? Somebody help me.
I think Black Friday here is the same day.
Okay, Black Friday.
Online sales are pretty much day after Thanksgiving.
Okay, so Black Friday is about the same day, and it's not some other special kind of party day where everybody parties the Friday before Christmas. Okay, gotcha.
That's St. Patrick's Day.
That's St. Patrick's Day, yes. Yes, definitely. And the green beer, and my colleague Robbie Burns is, just came from Ireland yesterday. He grew up in Ireland, so I think he can probably relate. I don't know. So we have a stack, a MVC stack. It's a servlet stack over here on the right. If you can see my pointer, can you see the pointer? Yeah, okay. And that's the traditional Spring MVC stack. It's built on the servlet API. It uses synchronous blocking I/O, and it works on top of servlet containers. And there's something called Spring MVC, which I talked about. Also, there's a flavor of data repositories called Spring Data, and it uses technologies like JPE, Java Persistence API, JDBC, Java Database Connectivity, NoSQL. But now there's a new stack. It's a reactive stack that's its counterpoint on the left here. And I'll go ahead and zoom in a little bit on it. But that's a non-blocking web framework, and it was built from the ground up to take advantage of the newer processors, the multiple core processors. And it was designed for reasons I just talked about, to handle ridiculous numbers of concurrent users. So what's underneath that stack is a non-blocking web server called Netty, or it could use Servlet 3.1 plus containers. And then there's a reactive stream adapter in there, because we handle different servers, so we need to be able to have reactive stream adapters for those servers. And then on top of that, there's, well, of course, Spring Security Reactive. That's a reactive flavor of Spring Security. Then we have Spring WebFlux. That's the reactive version, the reactive version of Spring MVC. And then we have Spring Data Reactive repositories. So far, joining the party now are Mongo, Cassandra, Redis, and Couchbase. And so those work in a reactive manner and a non-blocking asynchronous manner as well, with that back pressure that I talked about for flow control. By the way, yes, and please, if you have any questions as we go along, please do ask them. Yes?
Sorry, interrupting you, but
No.
is there any example of reactive stream adapters? Like what is that?
It's a layer of software that's internal to the project that then would take the layers on top and then just adapt it to the specific server. So every server has an API for making requests, and so that's all. It's just a layer of software. Yeah. And please do ask questions. This is actually, I created this presentation for you, and this is the first time I've given it. So this will help future audiences. If you ask questions, it'll help me gear this to future audiences. I'll know, what my audiences are thinking. And so that'll help us. Plus, in Leeds and in Edinburgh, please do ask questions on the Slack channel or on the Zoom channel. So the reactive stack, then, the reactive capabilities are in the web stack as well, in Spring, but also in Spring Boot. It's aware of reactive and helps in that regard. Spring Security, Spring Data, as I mentioned, and then the Spring Cloud. So, in fact, facilities like Eureka or registration or circuit breaker, those are reactive aware as well. Those work with reactive technologies. So one reason for creating Spring WebFlux or another reason, I guess, I've already talked about reasons, but another reason why it's a good time now, besides this proliferation of mobile devices and concurrent users, is that with Java 8 and Lambdas, it really enabled this continuation style of API, the Fluent API that has functional properties in it. And so using that is a good match for being able to put together functional operators as you process these reactive streams, and I'll show you that. We'll be discussing that in a lot of detail. In addition, Lambda expressions allowed Spring WebFlux to build another kind of endpoint. With Spring WebFlux, you can use annotations to define your controllers and endpoints, but also you can use a functional style to define your endpoints for your controllers, and we'll see that in a little bit. But now the question is, what does reactive really mean? So reactive actually refers to a couple of things. One is it's a programming model, but also it's for systems as well. There are reactive systems and reactive programming models. But regardless of which one it is that you're talking about, they're built around this asynchronicity, this non-blocking I/O. And typically what happens is with reactive systems anyway, it's an architectural pattern where you have distributed applications that then talk to each other through messaging in a non-blocking way, and they don't have to know where each other are. And then also with programming models, that's again non-blocking and uses back pressure. In both models, in both reactive systems and reactive programming, you're talking about, passing messages around and events, and then reacting to those events in a non-blocking way. And again, one of the important mechanisms in reactive is this non-blocking back pressure, this flow control. And with synchronous communication, you are blocking by default, and so that blocking gives you a natural back pressure because you're waiting for the response, and so it's kind of a natural way of applying back pressure. So now we have this thing called the Reactive Manifesto, and who's heard of the Reactive Manifesto, by the way? Okay, good. So what that is there were four authors, four people, developers, architects that saw that lots of different initiatives were being put in place to deal with this need for high concurrency and non-blocking. And what they decided to do was put together this document called the Reactive Manifesto, which provides kind of a common language and a common vision for reactive systems. And here's a link here to Reactive Manifesto, and I'll pull that up in a second. But the four cornerstones of the Reactive Manifesto is that today's applications in this environment of high concurrency needs to be responsive. So it used to be that it was good enough for apps to maybe come back in a half a second or a second, and now it's very typical. Users will get impatient if it's not very, very sub-second. But even in the face of a massively distributed systems, it needs to stay responsive. And so that's kind of the key point. And then to do that, there's a couple of ideas. One is being resilient. In a distributed system, if something goes down, we need it to be resilient to failure. Also, it needs to be elastic. It needs to, as we have more concurrent users, need to be able to scale up the distributed system so that it can ebb and flow. It can expand and contract to meet the demand. And then at the bottom here, it needs to be message driven. So the different pieces of this reactive system need to be able to talk to each other through messages in a non-blocking way, and to where the different pieces of the distributed system don't have to know where the other ones are. They can just send messages and then receive responses asynchronously. And so here's, just so you've seen it, here's the Reactive Manifesto. And it's a very short document. And one of the nice things is that it not only defines this common vision, but it also defines a common vocabulary, like what is meant by scalable, what's meant by failure, even what is meant by users. And so it talks about reactive system, what they are, and then talks about different features of that in a common vocabulary. So if you have the slide deck, and I'm going to make a PDF of this slide deck available, then you can follow that link. Otherwise, it is reactivemanifesto.org. So the difference between reactive systems and reactive programming is that reactive systems are an architecture style in a distributed system with the kind of qualities that I just talked about. And then reactive programming is this, it's actually a subset of asynchronous programming. Who's dealt with asynchronous programming, callbacks? Anybody that's dealt with JavaScript has probably done that. Who's experienced pain with dealing with callbacks? Anybody? Okay. And so asynchronous systems asynchronous programming is kind of hard, especially as you get deeper and deeper into it, more and more levels of asynchronicity. You start to lose track of what could possibly call you back, and so there's something called callback hell, right, where you have so many callbacks and you don't know where they're going to come from and you lose track. There's also something called completable futures in Java, which is a great improvement, but still can be a problem. Can have problems if you stretch it. If you have too many completable futures. So what reactive programming is this way where rather than having to deal with the nuts and bolts of asynchronous programming, what you can do is create streams. You can have streams that then has flow of events or elements in it that then you can subscribe to these streams, and then you can think of in terms of these streams of elements rather than, and then you let the underlying stacks, the reactive stacks, then deal with the asynchronicity, which helps a lot. By the way, here's a nice link from Jonas Bonnet and Victor Klang about reactive programming versus reactive systems. So some of the reactive programming use cases are external service calls. Like if you have a system where you have lots of microservices and you're calling one, but then blocking before you come back and then call another one, then any latency then adds up. And so, but contrast that with asynchronously calling external services. So you're calling, but then you can come back right away knowing that the response will be delivered at some point. And you don't have to manage all those callbacks, but you know that they're going to happen. Or you'll be notified that there's an error. So you can scale up, you can save a lot of processors and threads by using reactive in this for where you have lots of external service calls. Another one would be a case where you have maybe streaming data. I'm losing the screen here. Or you have streaming data where it requires high concurrent number of consumers to keep up with that demand. That's a perfect use case for reactive programming. And then even spreadsheets. The idea of reactive is reacting to changes. And so updating values in a spreadsheet or a spreadsheet-like application where one value is dependent upon maybe a couple of other values as it flows through a stream, then that's a good application. And then the ability to abstract over asynchronous programming is a good use case. And here's a link at the bottom by one of our colleagues, David Sire, about reactive programming, and he had a 3-part blog post about the reactive landscape, and he talked about these 4 points. So a very brief history of reactive programming in Java. Reactive ideas have been around for a long time. If you've heard of who's heard of the language Erlang? Okay, yeah, and then in libraries like reactive extensions for .NET, rx.net. And that was in the 70s. A guy by the name of Eric Meyer created that. I keep losing the screen here. I'm not sure why. Then there's an open source RxJava project. It's called Reactive Extension for Java, and that helped move reactive programming forward on the Java platform, and that was just a few years ago. And then there's something called the Reactive Streams Initiative. So there were so many reactive projects out there, or so many reactive infrastructures being proposed and being worked on, that some engineers with Kazing, Lightbend, Netflix, Pivotal, Red Hat, Twitter, and others then decided that it would be a good idea to standardize an API so that reactive infrastructures, reactive programming infrastructures could then be standardized on a particular platform, and that way they could interoperate. And so that happened with different platforms, particularly with Java. And so there is a Reactive Streams initiative for Java. And I went ahead and clicked that link. Here it is right here, Reactive Streams. And as a result of that particular effort, in the JDK 9, there's a class called Flow, which then has 4 inner classes that defines 4 classes that are in that standard. And so now developers that are developing reactive capabilities, reactive libraries, can then make them interoperable with each other by using those standards. There's also RxJava. There's Project Reactor, which is a pivotal project that is underneath our capabilities for reactive with web, with Spring Framework. There's also Spring Framework 5, as I mentioned. Lots of the pieces of Spring Framework 5 are reactive. There's also Ratpack, Akka by Lightbend. There's Vertex. So I'd like to focus now on what reactive streams are. That was that initiative for creating a standard and specification. And so it's for stream-oriented libraries. So streams, elements being messages and events being streamed that could potentially be unbounded. A stream of data could be infinite. It could never end. And so reactive streams needs to be able to handle that situation even when the stream doesn't end. And it needs to process them sequentially. So underneath the covers of a reactive library, if a stream has elements of a given order, we don't want that order to be changed. We need to be able to process them sequentially. And then we need to be able to asynchronously pass elements between components. So we don't ever want to block in a reactive system. We don't ever want to block. And then we need to have this back pressure. If you're streaming data between a publisher and a subscriber, then you want to be able to push back, apply back pressure if you're asynchronous, because there's no natural back pressure going on like it would be if you were blocking. Any questions so far, by the way? Okay. So this Reactive Streams API for Java then enables that interoperability. So there are 4 interfaces. One is called Publisher, and that's the origin of a stream. So a publisher, just like publisher, subscribe, a publisher would be the origin of a stream and would publish a stream, and you can subscribe to that stream by calling the subscribe method. And then there's a subscriber, so that's the other end, that's the consumer. And you can then say, okay, I want to subscribe to this particular publisher. And then when events or elements start coming on that stream, then you get one of 3 different callbacks. We have the onNext event, which means there's another element available, and so then you can react to that event. Also, there's an onError event if something happened. And then when the stream is complete, you're at the end of the stream, then the onComplete method will happen. So then there's also an onSubscribe. That's something that happened a little later in the reactive world. The onSubscribe allows you to be able to be called back when the subscription actually happened, when you've said subscribe to the publisher. You get this event and it passes a subscription. So here's the subscription, and the subscription then has two methods, request and cancel. So as a subscriber, if I've subscribed to a publisher, then I can, to control back pressure, I can say, I request 2 elements, or 5 elements, or 100 elements, whatever I want to be able to handle. And then that frees the publisher to then send that number of elements. And also I can cancel a subscription. So those are the 3 of the 4 interfaces in the API. A fourth one, which is not used as much, is called a processor. The processor actually extends both subscriber and publisher. And so you might use that if you have some type of intermediate processing. So you might subscribe to a publisher, maybe get a stream of data, and then manipulate it in some way, and then kind of repeat that, send it to other subscribers. And so you could act both as a subscriber to some publisher, as well as then act as a publisher to other subscribers. Okay. So here's a kind of a pictorial. Yes, please. No, please. I welcome your questions.
If there are multiple subscribers and each subscriber requesting different number of elements, how does publisher would keep track of this? It has published this many elements to this subscriber and this many elements to different subscribers.
Okay.
Because in traditional publishing, it doesn't keep messages on. It just starts publishing basically.
Okay, so the question is, if you have a publisher, and then you have more than one subscriber subscribing to that publisher, then how does it keep track on what it sent, what it hasn't sent? And so the answer to that question is, there are various ways that a publisher can work. So you might define that a publisher has a stream, and no matter what subscribers subscribe to that, maybe when an element is emitted from that stream, in one way of doing things, that element will never be emitted again. And so a different subscriber, if it gets an element, it's going to be different than that first one. And so that's one model that you can configure. Another model is no matter how many subscribers that you have, each one is going to get the same data. So as they make requests, the stream starts over for each subscriber, and so it's able with these standards to be able to handle both, and you can configure both. Very good question. Thank you. Yes.
So in that case, just following up on this question, then subscription, would all subscribers have the same number of requests in terms of like the number of elements that they're expecting in their request?
So the question is, I'm repeating the question for the audio. So if you had multiple subscribers for a particular publisher, then each subscriber, based upon their ability to handle data, might ask for different numbers of elements in their requests. And so if it's configured one way, where any element can only be sent once, then those subscribers asking for different numbers of elements will receive different elements, but different numbers, but in the same stream. Nobody gets the same elements. In the other way, where the publisher is emitting elements regardless of regardless of how many subscribers there are. The subscribers aren't going to exhaust a particular element because in that way, another subscriber would be able to get the same element, but it could ask for different numbers of elements based upon its ability to process. I didn't catch your name, by the way. I met about everybody, but you walked in a little later.
Julius.
Julius, good to meet you. Thank you. Thank you for coming to the session. And so here's a link to the flow class, which has 4 inner classes: publisher, subscriber, subscription, and processor in the Java 9 JDK. So a couple of diagrams that show a reactive system, different nodes in a reactive system, with a use case here. The use case is we want to stream from maybe a JSON stream, maybe at a high rate of speed, and we want it to end up in a database. And so in this scenario, we've got this stream coming in. The server is doing non-blocking reads on that stream. So it's not waiting around for data to come in, but it can read it in a non-blocking way. Then it goes through a reactive adapter, and then we have this flux. And I'm going to talk about what a flux is, but basically a flux is a publisher that can have multiple elements in it. And so the flux then goes to Spring WebFlux, which then goes to the controller in the MVC or Spring WebFlux sense, and then goes to the data repository. And so each time, as we get data in, then, and doing the non-blocking read, as we get data, then we call the onNext method. Remember, there's an onNext method. I'm going to go back to that slide. See, here's the onNext method of the subscriber. So this repository has subscribed to this stream, and then so as elements come in, we call the onNext method, and then to Spring WebFlux. Spring WebFlux then calls the onNext method in the controller. Controller calls the onNext method of data repository. Each of them are getting these events that says, hey, there's more elements here, or there's another element here. And then the data repository, if it's getting too much data to be able to handle, then it can apply back pressure. And it can say, okay, I can handle 3 more elements. Give me 3 more elements. And then that gets sent from the controller to the Spring WebFlux, which gets sent to the reactive adapter, which then will allow more elements to come in. But it's not blocking. So that the whole thing, front to back, then, is this back pressure controlled non-blocking way of ingesting data into a data repository. Okay, questions on that? Okay. And these capabilities are all baked into Spring WebFlux and Spring Reactive So it just comes out of the box. You don't have to manage any of that. We will deal with things at a higher level where we don't have to work with so much, we don't have to worry about the asynchronous stuff. We just think in terms of streams, and I'll show you how we do that in a second. This, by the way, is from an excellent article by Rasen Stoyanchev in Reactive. It's an InfoQ article on servlet and reactive stacks in the Spring Framework 5. So we could do that backwards then. We could stream from the database to the server and to some consumer, some subscriber that is streaming from the database. So let's say we had this where we're streaming to the database, and then we tail that database, right? So we have a high rate of data coming into the database, and then we're tailing it. And we're saying, okay, database, please stream me your data. Stream me all your latest data. So we can do it backwards here. And so it's exactly the same picture, only here we're doing a non-blocking write out to the output. And so as the data repository, as we request data through these chains, through different components, and we say, okay, I'm ready for some more data, then the data repository is going to then deliver those elements in the stream through these onNext methods. Again, using this API that's in the Reactive Streams API. And that way, we can go the other way between the repository and sending a stream in a non-blocking reactive fashion. Questions so far? Okay. So underneath the covers then, this with Spring WebFlux, underneath has to be some reactive programming library. And there are several. I showed you on this slide here. Let's see, it's right there. There's several RxJava, there's Akka, things like that. What we use in WebFlux by default is it'll work with others, but what we use in the preferred library is one that we are creating as an open source product called Project Reactor. So it's the reactive library of choice for Spring WebFlux. So Project Reactor, one of the goals is to avoid what's called callback hell, right? Where you've got all these callbacks and you can't manage them. And other, completable features, other ways of doing asynchronous programming. So reactive libraries like Reactor address those. And it also focuses on additional aspects of being able to do reactive streams. Like, for example, it allows you to fairly easily compose streams and compose operators that process these streams that we talked about, like that stream of data, for example, in a readable way. One of the goals is to be very readable. It's very important to be able to write code that is readable, of course. So another goal is for data to be thought of as a flow of elements in a stream that we can use a nice vocabulary of operators to be able to manipulate. And you'll see some of those operators in a minute. Another important capability is that we don't want anything to happen until we subscribe to a stream. So we don't want any demand to happen on a system until somebody is interested, until there's a subscriber that's interested in receiving the elements that are in a stream. So you can set up a publisher, but until you subscribe, nothing happens. You haven't taxed the system at all. And then, of course, we need to have, in Project Reactor, as with any reactive library, it needs to be able to apply back pressure in case you're receiving too much data. And there needs to be a high level of abstraction over asynchronous programming, so we don't have to worry about the asynchronous stuff, but it also has to be deliver high value. And it's concurrency agnostic, so we don't want to, as developers, developing reactive programs, we don't want to have to worry about the concurrency model underneath. So there's publisher. That was one of the interfaces. And with Project Reactor, there's actually two types that implement publisher. One is called Flux. So Flux implements publisher. Now Flux is a publisher that has multiple elements in a stream. And then there's another reactive type called mono. And mono can have either 0 or 1 elements in the stream. And so, one classic case for mono might be maybe you have a web page and you want to show the fields of some class, and we'll see that actually in an example. You want to see the fields in in a class. You might put that class, an instance of that class, as an element in the stream in a mono, since we know we only are going to be showing one instance on the screen. So we would probably use a mono, but it implements publisher as well. So it has those same methods that the publisher has. And we can subscribe to it. So here's just a pictorial of mono. Mono is just 0 or 1 elements in a stream. And flux is 0 to many elements in a stream. And both of those have generic types. Mono and flux have types. Those types are the type of element that is in that stream. If the type of element is a string, for example, then you would see the generic type of string. In our application, we're going to have a type of card. It's going to be card, like playing cards. And so we would have mono or flux of card in some of our classes, in some of our streams. Okay, questions on anything we've talked about so far? Okay. So here's a simple example of programming in Project Reactor. We can create a flux with the flux class. We're going to use a static method of the flux class called just, and then we're going to give it, one or more arguments. Here we're going to just say hello Reactor world, and then remember, nothing happens until you subscribe. So there's a method called subscribe on Flux, in which I can pass it a lambda expression, which will then take the elements like hello Reactor and world and pass it into that lambda, and then our lambda expression, our function, is going to then take that element that got passed in, and it's going to print it to standard out. Right, so the output would be hello Reactor world. And so, so I'll go ahead and run that in IDE here, just to kind of show you that. Here's our program. In the main, we're going to just do what I just showed there. Here we're going to use a method reference. Who's familiar with Java 8 lambdas and method references, things like that? Okay, good. So I could say here, well, I want to make replace this method reference with a lambda. So that's the lambda we just saw, where we're passing a lambda expression, which is a function which takes something and then returns that something. Actually, it doesn't return anything, but it has a side effect of printing it to standard out. But that can also be expressed as a method reference, just a shortcut. So if we run that, then our output would be hello Reactor world, and that's awful small to read. So I'm going to view it in projector mode. Let's see, view, enter presentation mode, just so you can see the output. There we go. Okay, so there's hello Reactor world. Okay, any questions on that example? Yes?
Is it all executed by one thread?
Okay, so the question is it all executed by one thread? That's a very good question. And the answer to that question is, it doesn't matter. You don't care. And it's nice that you don't have to care, because you don't have to manage the threads. Each element of the stream could actually be, is asynchronously processed. And so as your threading model, or your processors, or your cores, as they have the ability then to handle these elements in the stream, then that's managed for you underneath the covers. So you don't know and you don't care.
And can you like request only one element from this stream?
Okay, so the question is, can you only request one element from the stream? And yes, you can control that back here in, if we look at the API, go back to the standard, yeah, here we go. If I'm a subscriber, then if I've subscribed to a publisher, then in the unsubscribe method, I'm going to get a reference to the subscription. In that subscription, then, when I've subscribed, I can do requests. So I can say request 1 or request 5 or 100. So as I can request as many as I can handle. Okay?
How does the publisher send publish data? Basically, there's no function for publish.
Okay, so the question is, how does the publisher send published data? There's no function for publish, and that's a function of demand. So the publisher has this potential to send data, but it doesn't actually fulfill that potential, act on that potential until somebody subscribes. And then underneath the covers, when you send a request for a certain number of elements, then it, in its API, or in the implementation of its API, then fulfills that as it's able, and calls the onNext methods, or onError or onComplete, as it sends that data. Yeah.
So when you implement, there's no way to how you package data for publication within the publisher then?
So, repeat the question, please. I'm sorry.
Let's say, for example, the publisher has a subscriber. Just like to show us with the demonstration that you have a stream coming in, and the webhook is taking it and publishing it to somebody else. So it's basically a subscriber and a publisher. So in that case, he will subscribe. So once he gets the data, if he needs to maybe transform the data before he sends it along, where would you do that in an implementation?
Oh, okay. Okay, so the question is like on processor, if I'm both a publisher and a subscriber, so I could subscribe to a publisher, but then I could put on my publisher hat and say, okay, I'm a publisher, I'm going to publish that data, and then it will use then operators, which I'll show you in a minute. That's a missing piece here that I'll show you in a minute. That then allows you to use, let's say I'm a flux, right? I can publish multiple elements. There are lots of different operators and methods in the flux class that allow you to then generate or publish things. So that's a very good question. I just haven't got there yet.
Thank you.
Yes, quite. Oh, you're welcome, Julius. Very welcome. Yes.
Back in the slide where you had the web server getting a stream of JSON data.
Is it this one? Okay.
So if the stream has a much higher rate of transmitting data from what we have configured with the back pressure, that means that the web server can be overflown basically by data, right?
Okay. So the supposition then is, the assertion is that if the server isn't able to handle as much data as being sent by the repository, then I could get an overflow, right?
Or actually the previous slide where the data were coming into the server, yeah.
Yes.
Let's say that the data repo couldn't handle the amount of data, so for some reason then we had to configure the back pressure on the reactive components to a much lower rate from what they're being transmitted in the JSON.
Okay, so for the audio here, the question is, let's say that it's coming in at a very, very fast rate, maybe 1 million elements per second, let's say, and the database can only handle 1,000 elements per second. Then as it's coming in, we're doing these non-blocking reads, and we're presenting, you know, the next elements that we're getting. But the data repository, built into that data repository, or any subscriber that you would write, or that, you know, that's in some infrastructure like a data repository infrastructure, in order to not be overrun, then you can use the request method. So the data repository in the driver, in the MongoDB driver in this particular case, if it is being overrun with data, then it will wait until it sends a request again, you know, saying I want, you know, 10 more bytes or 100 more elements. It would just quit sending those messages here toward the stream until it's caught up. And then as soon as it's caught up and it can handle more data, then it would send requests for more data. And so it is, it's kind of pulling data, you know, pulling data through the system, saying, okay, I could take 5 more elements, you know, and so it's controlling back pressure that way. Now, in the case where, there is a case where, let's say that's not built into the subscriber. The subscriber, let's say, isn't smart enough, doesn't have the capability of knowing when it's, or maybe it doesn't care if it's being overrun. Then then overrunning is a possibility. So there are configurable items within reactive streams to where you can say, okay, in the case of an overrun, what do I want? Do I want the latest elements? Do I want the first? Do I want to keep the latest elements? Do I want to drop out the latest elements and try to preserve the older elements? What do I want to happen, right? But in this particular case, back pressure is managed actively by request.
But even if it's managed, isn't that the problem? Just propagate to the higher level components.
Okay, so even if it's managed, then what happens is, then it has to be buffered somewhere, right? And so you could run out of memory, you know.
So the server in that case can run out of memory and become unresponsive, right?
Yeah.
Even if there is back pressure.
Yeah. So if you've back pressured it, you know, that, and you wish to keep all of that, the stream of data, it's gotta, you know, build up somewhere. And so if the system, you know, that is handling all that, you know, underneath the covers in the reactive libraries or whatever, if you haven't given enough memory or whatever facility it needs, you know, then you could have a problem. But yeah, good questions. Yes.
So does it mean basically it's a different case of DDoS attack? So basically you can subscribe to a publisher with many subscribers, and they will consume quite less amount of data compared to the publisher's rate of transmitting data, and you can cause the server to fail.
Okay, so let's say that, so the assertion is that maybe I could cause a DOS, denial of service attack, by having too many subscribers to a publisher. So having a subscriber to a publisher, or have multiple subscribers to the publisher, doesn't impose any more you know, resource problems, as far as like, it doesn't have any more load on cause any more load on the publisher in that case, because all you're doing is requesting. You're saying, I'm ready for more elements. That's all you've done. You haven't caused the publisher to have to work any harder. All you're doing is saying that I can handle more elements. Now, if you had 100 million trillion subscribers saying, all calling the request method of one publisher, I suppose, you know, you could have a problem. But the act of subscribing and indicating that I'm ready for some more data, you know, doesn't normally cause a problem as far as load, you know, because nothing really happens until the publisher says, okay, you want 5 more elements? here's 5 more elements, and then it calls the on next with the next 5 elements. Okay, other questions? Okay. So we have our reactive types, our mono, our flux, and then we have our example, hello reactor world. Now we have something called marble diagrams. Now marble diagrams are these diagrams that help us understand operators in the reactive world. And so like RX Java or reactive extensions in general have, for every operator, there's a marble diagram that pictorially shows you what's happening in that operator. So here's a marble, I'm going to come back to this marble diagram. Here's one for mono. Remember that's the publisher that has 0 or 1 elements. Here's a marble diagram for flux, we'll come back to it, that has flux as a publisher for 0 to many elements. But marble diagrams, I just want to kind of show you what they are. So what a marble diagram is it represents the stream before it's being applied, before the operator is applied, and after an operator is applied. So here in a stream, we might have these elements, this kind of just fictitious elements. One's a triangle, one's an up arrow, and like the triangle came in at some time mark, 12 minutes and 51 seconds, and then the up arrow came at some time mark, and here's the end. And then we have an operator, and we'll just call it, it's just a made-up operator. It's called a flip operator. And so the triangle comes in and then goes through the flip operator and then flips over. That's the transformation that the operator did. It just flipped the triangle. And then we flip the arrow. And then we try to flip the circle, but you can't flip a circle. It's not going to be different. And so this symbol over here, this X, means that there's an error. So here a stream came in. We sent it through the operator, and this is the transformed stream. The stream after the operator has been applied. And so what we ended up was with 2 elements, and then that on error. Remember the on error method that's in the subscriber. Yeah. And so this is this mark right here. When you see that in a marble diagram, it means it completed, that stream completed. So there were 3 elements and then the stream completed. Streams don't have to complete. Remember I said that a stream could be infinite. You could open a stream and then a publisher just publishes forever. Maybe it's a stream of data from that you're listening for extraterrestrial activity, or whatever, and so it just keeps coming, and you keep waiting for it, and maybe you get some blips, and you get some data coming, but you never plan on closing that stream, so it's infinite. So you wouldn't ever have this completion. So you would never get an on complete. All you're going to get is on next or on error, as if there's some error. So that's the idea behind marble diagrams. And there's this site called RX Marbles that has marble diagrams for RX extensions. Now these marble diagrams are for different operators, and you can play with them. Like for example, here's a zip marble diagram, and we can play with these and see how 2 streams coming in might be zipped and then the output stream is those stream being zipped up. So you can play with those. Now these operators that are in these marble diagrams aren't, there's not a one-to-one between these and the ones that are in Project Reactor, but it's a it's a nice way to get used to marble diagrams and some of the the types of operators that are in reactive. With the documentation for Project Reactor, there is a marble diagram for about every operator that's in the Flux and Mono classes. So going back to the presentation here. So the app that we're going to use, I've presented a lot of theory, a lot of slides and bullet points, and saw a little code. But now we're going to kind of, as being developers, we're going to roll up our sleeves and actually look at a lot of code and look at some marble diagrams and understand these operators more thoroughly. And the app that we're going to use is one that I wrote called Reactive Card Magic. And the reason why I chose cards to represent, as a demo for reactive streams is that I thought that, as soon as I was learning about operators, and I saw an operator like zip, where we could take two streams and then zip them into one stream, I thought, well, that's kind of like shuffling a deck, right? And so if I, everybody's played cards, right? So if I took a deck of cards and I made two streams out of it, like a deck might be one stream, right? There's a stream of cards, and each element in the stream is a card. But if I split that into two, now I've got two streams that I'm shuffling, and now I'm zipping them. So that operator then represents, the active shuffling the cards represents the zip operator. And so, it's something that I can relate to, and that's why I created it. Maybe cutting the cards might be using other operators, or dealing the cards. Maybe I deal a poker hand, and I deal you 5 cards and me 5 cards, but I do them in an alternating sense. So those would all be operations things that I could model using stream operators. And so that's what we're going to do. So there's this application called Reactive Card Magic. It's open source. Right now I'm putting the kind of Apache 2 licensing on it, but it's in GitHub right now. If you reach out to me, I'll send you a link. I'll just go ahead and show you a quick demonstration of the application. Let me make sure that the server has, let's see, there's the card deck demo. I need to get it out of presentation mode, view, exit presentation mode. Okay. And I'm going to go ahead and, I guess it's running. So here's the client. I'll show you the architecture here in a little bit, but here's the client. Go ahead and reload it here. And it's basically got different functions down here that you would do with a deck of cards. Like I could get a new deck. So that's where I open up the package of cards and I pull it out, and if you've ever open up a deck of cards, you know that it comes in some natural order, like spades, diamonds, hearts, clubs, and they're all together. So that's a new deck. You see that okay? And then maybe I want to deal the cards out, but I only want to deal out one suit, maybe the hearts. So I could click that button and it would show me only the hearts, and in this case, only the first 10 hearts. Or maybe I want a new deck and I want to cut the cards. So cutting meaning, take a stack and put them on top of the other stack. And so maybe I have a new deck and I say cut the cards, and then it's going to do that exact operation. It's a little easier to see if I just show you these hearts, maybe 10 of them, and I say, okay, cut those cards. Notice that the bottom 2 cards got put on top of the rest of the stack. We just cut the deck. There's also an overhand shuffle. So I'll go only hearts and do an overhand shuffle. That's where we take the cards and kind of shuffle them overhand and taking a few of the cards and then putting them on top of the rest of the deck like that. So that can be that's what this overhand shuffle function does. And so notice that it started out ace through 10, but here then it put the 6 through 10 on top of the stack, and then the 2 through 5, and then the ace, and so it kind of did the overhand shuffle. There's a riffle shuffle. So if I have a new deck and I do a riffle shuffle, and that's the one where you take the cards here and then you do the bridge shuffle and you're mixing them up. So that would be, I'll take the riffle, I'll do that with this, and notice then that, I'll do it again here, notice that here we have half the deck with spades and diamonds, and then the other half of the deck has clubs and hearts. If I do the riffle shuffle, then the club, this ace of clubs should come right next to the ace of spades. The 2 of clubs next to the 2 of spades, etc. So that's the double hit there. And so if I do it again, this ace of diamonds should come up to the ace of spades, ace of hearts to the ace of clubs. So I'll do that riffle shuffle, right? If I do it again, then the 7 should come up next to the aces. Do it again. And so that's a riffle shuffle. That uses that spoiler alert, that uses that zip operator. And then we have a random shuffle where, I don't know if you ever played 52 card pickup or asked somebody, hey, you want to play 52 card pickup? And they say, yeah. And what you do is you throw the deck up in the air and then they land everywhere and you say, now pick them up, right? So that would be kind of a random shuffle. And then here we could deal a poker hand. That's where maybe I deal you this card, this ace of spades, and then I'm going to keep that card. And then I deal you the 7 of clubs, I'll keep that card. So I would say deal poker hand, and I should be giving you an ace of spades, a 7 of clubs, an ace of diamonds, 7 of hearts, an ace of clubs. So I'll deal that. And then also part of that is sorting it. So sorting it in ascending order. So I just dealt you in an alternating fashion some cards. And then the last one is shuffle deal. So I'm going to shuffle this thing a bunch of times, and then in different ways behind the scenes, and then deal. And so if you get bored with the presentation, you can actually just use this application and play poker with each other while I'm talking and win money off of each other if you'd like. But here we're shuffling and dealing, and then we're also scoring what has been dealt. So there's nothing special about that hand. And so we just go with the highest card wins, shuffle and deal. Maybe here we've got one pair of sixes. If we're really, really lucky, we'll get a straight or a straight flush or even a full house. There was 2 pairs and I clicked off of it. But anyway, that's the idea. So I'm going to demonstrate then these reactor operators in the context of this application. So that's where we're going. So here is the architecture for this application. So we have an HTML5 application down here, HTML5 client, single page app. And then we have some controllers. Here's a card deck controller. And then it's a reactive controller. It uses Spring WebFlux. And then we have some services on the services layer. Here we have a card shuffling service. And then finally we have this repository that holds a deck of cards. We've loaded it with this card deck data loader. We've loaded it with 52 cards into the database. And so notice that between nodes in this reactive system, like from the repository, when we loaded the repository from the card deck data loader, the way that we got it in there is we sent it we published a flux of cards. And then the data deck, card deck repository, it subscribed to it and then loaded it in. And then and then going back the other way, when from the client we say we want to be dealt some cards, we want all the cards, we want whatever, then we tell the card deck controller and then through this reactive streams capability, the request gets to this card deck repository that we want some cards, we want a certain number of cards, whatever, and then we get streamed from here to here. We've published here a flux, and then we get streamed this flux of cards to the card deck service, which then finally gets delivered over JSON to our front end. Now remember when we dealt a poker hand and we wanted to be able to find out what kind of hand that was. Well, that was through this path right here where the card deck controller said, okay, I've got a poker hand, tell me what kind of hand it is. And so it went to this poker proxy service and said, for these cards, these 5 cards, what kind of hand is that? And so then it used this thing called a web client from this application, which in an application then acts like a reactive web client, and it requested from this endpoint, it gave it a flux of cards, and it requested, what is the name of that hand? And so then the poker controller called the poker service, which then scored the hand, said, well, what kind of hand is this? And then also put it into this hand frequency repository to where every time a hand is identified, it is classified, it's put away into a repository so we could later get a frequency distribution of what hands were dealt. So anyway, it's an application that has controllers, services, uses fluxes and monos, reactive streams to be able to asynchronously with non-blocking back pressure be able to pass data around, and so that's where we're kind of going to be playing here. So getting a new deck, yes.
Does that mean WebFlux basically writes from the server to the front?
So WebFlux is Spring WebFlux is a capability related to like Spring MVC, kind of the counterpoint, the reactive counterpoint to a Spring MVC, where you can create a controller, and you can then make a request of a controller, etc., and then your controller then, or your service, whatever, could act as a publisher, like of a stream, like of a flux or a mono, and then it could act as that publisher, and then as soon as somebody subscribes to it, like like another piece here, like this proxy poker service subscribes to this flux that was in the poker controller. Then, as soon as somebody subscribes to it, then it could then respond to that by streaming the cards. So the publisher then, the flux, has that capability of streaming, and so Spring WebFlux allows that to occur in a reactive way. Thank you. Yes?
I don't know if you're going to cover it later on. Usually most of the frameworks give you an ability to, when you interact with a blocking non-reactive layer inside your web server or something, to wrap it basically and pretend that it's reactive somehow. And usually there would be a thread spawn in the background waiting for this blocking response to come back, and we'll pass it back to your reactive component. So what does the Spring Flux provides when you actually have to interact with a blocking component, which you cannot, it's a legacy component, let's say you cannot change it to be reactive.
Okay, so the question is, let's say that you have a blocking server, a blocking controller. Maybe it's Spring MVC, but you want to interact with it in a reactive way.
Or the database is blocking, you cannot change.
Or the database is blocking, and you want to interact with it in a reactive way. So either way, then, like for example, with Spring WebFlux, there's something called a web client. And so let's say in this poker proxy service, maybe this poker controller was Spring MVC, and so it was blocking. But the web client is reactive. But it can work with blocking services. And so from the standpoint of my poker proxy service that uses the web client class, I can go ahead and use it and in a reactive manner. But then when the web client itself hits that blocking controller, then it knows what to do, and so that's the same kind of thing. Similarly with the data repository, if you used the standard like JPA data repository, then your active system then would have to block. But it would know, if you used, I haven't actually tried this, but you would have, like for the repository, you would need to use, with Spring, you would use, data repository classes. And by doing that, then you know that you're going to have to block. But the application, the piece, the service that you use to actually get data from that data repository, it knows, that it's using a non-reactive data repository, and so it would have to expect to block. But so you can have a mix of reactive and traditional in the same application, and so it'll handle that. It'll then handle that under the covers, and will block when it has to.
Can you wrap those calls with a layer that will pretend it's reactive?
Okay, so the question is, could you wrap the code with a layer that pretends to be reactive? I'm sure that you could do that to try to maybe even using that processor or something, or you could probably write your own layers to abstract that away a little bit. Sure. Okay, so. Getting a new deck, and that was where, remember, we hit new deck and then we saw all of our cards. So here is, if you're familiar with Spring MVC, this is going to look very familiar to you because we've got all the annotations that we have in Spring MVC, only this is a reactive controller. So we have at-rest controller, same as Spring MVC. Request mapping, that starts to define our endpoint. And, we have a class for our controller. Here we're injecting a card deck service into it. And then we're getting a mapping. So we're saying, okay, the endpoint then is going to be /new on top of cards and deck. And we have a method, getCardDeck, that then is going to fulfill that request. It's going to be the method that actually gets called when you hit that endpoint. And then then we can say, okay, what are the request parameters? Well, one of the request parameters is num cards. How many cards do I want? The default being 52, like in a deck. But we could override that if we wanted to in the get request. And then here we use some operators like take, collect, list, and map. Those are all some reactive operators that are in Project Reactor that allow us to then take this mono of card hands, which is 0 or 1 card hands, card hand being an element that represents a hand of cards, which would be the individual cards plus the name of the hand. And so as far as like an annotated controller, it all looks the same as Spring MVC, except for we're returning some publisher, some reactive type, either a mono or a flux, with some generic type, card hand or whatever. And then in our method where we are using reactive operators like take, collect, list, and map. So to switch from doing things like an application from Spring MVC to making it reactive, as you can see, it's like on the surface very easy. It's the same annotated controller, except for you are going to introduce some stream types like flux or mono, and that you're going to return those instead of returning some other things. But other than that, it's quite an easy switch. So it's very easy then to, if you're playing around with, if you've got a Spring MVC application, maybe a small one at first, to kind of think in terms of, okay, how would I move that into reactive? It's nice that that Spring WebFlux uses so much of the same controller annotations to make it easy to switch. Questions? Okay. So now here's a functional endpoint example. So we saw a controller with annotated, an annotated controller. With, as I mentioned before, with Spring WebFlux, there's this new kind of way that you can define an endpoint for reactive, and that's called functional endpoint. And so here we have a bean, and what you do is you create, you return, or you have a router function called new deck routes, and here we're passing in any dependencies we need, like card deck services, and then we have default number of cards. Remember, like in the, bless you, in the annotated controller, we had default number of cards as 52. Well, here we're just setting the default number of cards to 52. And then to actually define the routes, we are then using request predicates, one being get, new deck. We're going to say the route is /new deck. And then when a request comes in, we're going to take that card deck service and generate a bunch of cards using the same kinds of operators that we used for the other one. And I'm going to walk through what those operators are. The key point being that you now have a choice when you deal with reactive. You can either use the annotations, the annotated server, or annotated controller, or you can use a functional endpoints. So you have a choice. With functional endpoints, it may look a little harder to set up, but you have more flexibility on getting exactly the endpoints you want, and it's in a functional style if that's what you want. So then there's also, I mentioned web client, and I showed you that in the system architecture diagram. So what that is it's a way in your program in Java to be able to say, okay, I want to hit a controller, but I want to do it in a reactive way. And so web client is what you would use for that. It's reactive, it's non-blocking, and it uses a functional API style. And it does all the back pressure thing. And so it's like REST template, if you've ever used REST template in Spring MVC. Use this for the same purpose, except for web client is the reactive version of web template, a REST template. So it's non-blocking, reactive, and it supports higher concurrency. So kind of under the covers, because of the non-blocking aspect and the way that web client is written, then it can hit that endpoint, hit the service, the server, with in a reactive way. And then it also provides a functional API. So when you write a web client, or when you use web client, you use a functional API. And as my colleague here asked, what if you're hitting a blocking server? Well, web client will support that. And then you can stream up or down from a server. So when you use web client to, maybe you're going to do a post, you could stream a flux, let's say, as the body of a post, as the payload of a post. Or the other way, the response could be some stream of cards or whatever. So here's a use case. Yes?
Before you have a stream of elements that shows the data going to the data store and back. Where's the web client in that?
Okay, so before we had this diagram back here. So where's the web client in this? And so in this case, I mean, under the covers, they might be using a web client in the infrastructure, and probably are in various places, but there's not explicitly any web client. Now let's say that let's say I was hitting that server. Maybe I'm external to that server. And that server is either defined as a control, an annotated controller, or as a functional endpoint now. And I'm external to that in a Java program. And if I wanted to receive that JSON stream that's being streamed, then I could use a web client to hit that controller. And then it would reactively be able to stream the data in a non-blocking way.
So the client should be your front end?
Yeah, the web client could be a front end of that if I'm, have a Java program, as opposed to like a browser or something. Yeah, exactly. Good question. Thank you. So mono, and then we see flux. Here we go. Okay. Review. I could go straight to the slide, but helps to review every once in a while. Flip. Next time I will go straight to the slides. Okay. Reactive marbles, our application architecture, annotated controller, functional endpoint example, Spring WebFlux, identifying a poker hand, calling an endpoint. Okay, so remember in the diagram, when we wanted to identify a poker hand, we used the web client to call an endpoint, to call a controller, or a REST endpoint. So here, to use that web client, what we do is we use the create method, the factory method of web client, and we pass it in this is one way of doing it. Of course, in the real world, you wouldn't do it this way because you want to externalize all your configuration. But in this little toy example, for the slide, I went ahead and hard-coded the URL in there. So we're creating a web client that is going to make its request on that particular URL. And then to actually invoke our request, we need to choose, okay, is it going to be a GET request, a POST request, what? So here we're saying, okay, we want a POST request. The URI that we tack on to the end is going to be /poker/ID hand. And then the body, the payload, the body that we're going to send to the post is going to be a stream of cards. So here we're saying it's a card flux. So presumably somewhere else we've created this flux that contains these cards, and then here we're telling it what kind of thing we're streaming. So that's going to execute the post, And then we're going to retrieve from the server, and we're going to take the body that comes back, and we're going to convert it to a mono, and we're expecting a stream, which is, what kind of card hand this is. Is it a straight flush? Is it a, two pairs? And so this way, using web client, using this code, we can make a reactive call in a functional style, non-blocking with all the back pressure to our identify a poker hand service. And so in this application, this reactive card magic application, actually we're using monos and fluxes, and these are the operators that we're using. I just went through and every time I used an operator, I went ahead and cataloged it. So we're using all these different operators like mono. There's a flat map here. There's a map. You might be familiar with those from, or their counterparts from the Java Collection Streaming API. And then on the flux, we're using more of those. Things like map or take a number of cards, filter. So I'm going to walk through some of those, but those are the operations that we're using in this application. So here's a use case. We deal 10 cards of the same suit. And I showed you I hit only hearts, it dealt those cards. So here is the annotated controller that responds to that and deals those cards, that sends those cards back. So so what we send it is some suit, hearts, clubs, spades, diamonds. And then what's going to get returned is a mono of type card hand. Card hand has the 5 cards that are the cards that are in it, and then the name of the hand. And so the method is get card deck by suit. Here we can, with the path variable, we can say, is it heart, diamonds, clubs, or spades? And then how many cards do I want? Yeah, how many cards do I want? So then we're going to use this card deck service. We're going to use this generate method, and that's not an operator, or that's not, this generate method isn't an operator, isn't like a flux or mono operator. There is one name generate, but we're kind of overloading it, so don't have to worry about that one. Here's the first one. It's called filter. And what that does is that takes a function here as a lambda expression, and it's taking the card, and we're saying that we want all hearts, and so it's going to filter. It's going to take the card that it got from that stream, and it's going to get the suit of that card, and it's going to check to see if it equals the suit that was passed in to the function.
So it's generate method, is it returning all the cards, all 52 cards?
Actually, okay, yes,
Yeah,
I'm sorry.
Is filtering, yeah.
Yes, the generate method is returning all 52 cards, thank you. But it's not a flex operator, it's just some method that I coded into the card deck service. Thank you. So here we're filtering we're only allowing the cards to pass through that are of our same suit. In this case, hearts. And then we're going to use the operator take to only take the first 10 cards here. If we didn't override the default value, it would take the first 10 cards. And so these two are operators on methods on the Flux class. But then we're going to, and here's one called collect list. Collect list is a method on the Flux class. It's an operator on the Flux class. But what it does is it takes the stream, in this case a stream of cards, and it's going to collect them into a Java collections list. And so now what that returns, collect list returns a mono, because there's just one of them. That mono contains a list, in this case a list of cards. And then we have a map that's going to take that mono, which contains a list of cards, and so it's going to pass into the function that list of cards, and it's going to map it to a new card hand with that list of cards as the first argument and a string as the second argument. And that's why we see the word only hearts, because it had only and then the hearts that were passed in. So any questions on that? So now we're really kind of getting into some code. So I want to make sure that we're all on equal footing on this, this code that we're walking through. Okay? And so these are the interesting parts that have to do with reactive streams, Project Reactor. So the first one is a filter operator. Remember that there's the filter operator. So you all know what a filter operator is, probably from Java 8. So all it does, here's the marble diagram. It's the signature is filter. You pass it a predicate. A predicate is a function that will return true or false. In this case, if it returns true, you let that through. So here's the and it returns a flux. So it returns another stream of the elements that actually, match the filter. So here in the marble diagram, you have all these shapes that are coming in, and but we have a filter on circle, and so it only, the only output on the output stream are the ones that are circles. In our case, the only ones that are going to be output from this operator are the hearts, if we passed in hearts. Okay, you with me so far? Okay. So then the next one is the take operator. Yes?
That scenario, you have the end of the string. If it was a continuous string, what would you use?
Okay, so here...
You can't filter on a continuous string.
Here we have an end to the stream, right? What if we had a continuous stream? Well, if we had a continuous stream, then the output would still filter, but until we hit the end of the stream, we're not going to have the end of this stream, right? So it would just keep filtering, but it would do it in a non-blocking way, okay? It's a good question. So now we have the take operator. So here we have the take. We're going to take 10 cards, let's say. Here's the marble diagram. We have some cards coming in, and then we say we're going to take 3, take 10 in our case, and that's just going to take the first, and it's going to take 3, and it's going to complete. Okay? And then we have the collect list. As I mentioned, collect list takes a flux of elements, but then it's returning a mono of a list of elements. So this little circle, or this little rounded shape, that represents a list. So it took the elements that were in the flux, and then it created a list, and then the elements got put into the list, and then as soon as this stream is done, then it's going to return this stream. So it's going to complete that stream. Okay? And so then finally we have the map operator. Well, map operator, in this case, it's the map operator on which type? Is it mono or flux? Mono, because the collect list took a mono. So we're doing the map operator on a mono, and we're passing in, in this case, we're passing in an element of a list, and then we're returning a new card hand. So here's the mono map operator, where we're taking a function in which it's a mapping function. In this case, we're element of a list, and we're mapping it to a card hand. So there's the map operator there. So pictorially, what's happening, if we look at the top here, we have this flux of cards, as my colleague pointed out. In the flux of cards, we have 52 cards coming in. We're going to filter on hearts. So it's going to pass the filter only if it's hearts. This should be a 10 here. We're going to take 10. We're going to animate this in a second. We're going to take 10. We'll end up with 10. And then we're going to collect list. It's going to collect those 10 into a list of a mono of list of cards. And then we're going to map those to a new card hand with only hearts. And so that's going to be mono card hand. And this represents that mono of the 10 cards and the words only hearts. So I'm going to animate this, but I want you to watch the non-blocking behavior. So you would expect, as this was animated, for maybe the filter to apply to all of these, and then for all of those to be filtered into this before the 10 are taken and put here, and before the list is collected and put here. But remember, it's reactive and non-blocking. And so what really happens is that as these are filtered, then let's say that the ace of hearts goes through. The ace of cards, hearts, if you watch it, is going to actually pass through the filter and immediately be taken and put into the collect list. But then it's going to stop there in the collect list, and you'll see other things going through. And it's not going to get past collect list until it's got all 10 of them. And that is because, we need to pass a whole mono into this thing, into this next. So collect list doesn't, you're not ending a collect list until the stream ends. So anyway, watch the behavior here. Okay. See the ace of hearts come in, past the filter. And notice the take is decrementing. It started out with 10, but it's going to go all the way down to 0. So now that the take has gotten through all of the ones that it needs to take, so it's done. And so now it sends an on complete, or a cancel, I'm sorry. It sends a cancel to this publisher and says, okay, I don't need any more. I've got, I'm done collecting my list. And it's going to send a cancel upstream, which is then going to be received by, going to get propagated all the way to the publisher. And so we'll see these disappear. But also, once it's collected the list, it's going to send an on complete downstream saying, okay, I'm complete, now we can proceed. And so these disappear, and we completed, and so then the map was able to finish, and then now we have our mono of card hands. Questions on that? Yes?
So according to that, you don't need to complete on the flux.
So according to that, what?
According to that demonstration, you don't need to complete on the flux then. You could just have your flux code, since you know the number of items you're looking for, you could just take it and then.
Right. So according to that, you don't have to do a complete on the flux. The complete on the flux happened, but it happened underneath those operators. So it happened as a byproduct of using those operators. So those operators, like the interfaces like publish, subscribe, subscription, etc. Those are all low-level things that the reactive library uses, but rarely do you have to use them as a programmer. As a developer, you use the higher level operators, of flux and mono to get your job done. And underneath the covers, it's nice to be aware that on next and on completer and all those things are being called, but you just deal with the higher level abstractions. Okay? And so one other, so I'm going to get through one other kind of animation use case here. before we start to wrap up. I know we've got about 6 minutes left. So dealing a poker hand alternating. Remember we deal one to you, one to me, one to you until you have a hand. I showed you that already. So this is the code for that, where we have, first of all, we have a comparator. We want to be able to sort, once we've given you a hand, I'll go ahead and just run it really quickly. If I shuffle and deal a hand, notice that not only do we deal the hand, but we also sort the cards in their natural order. And so, so to do that, we need a comparator. So the sort operator is going to take a comparator, which is going to take the value of the card, the worth of the card, no matter what suit it is, and aces are going to be the lowest, and kings are going to be the highest. So that's what this is. So here is the method then, called deal poker hand, that's going to take a flux of cards, in this case, maybe our 52 cards, or maybe just the hearts or whatever, just some cards, and then we're going to deal them, and we're going to return a flux of cards. So we take that flux of cards that we were passed, and we do an index on it. Now I'm going to describe in a minute, I'm going to show you a pictorial of what an index is. But the reason why we're doing the index is because we want to alternate these cards. And so in this particular case, the way we're going to alternate those cards is we're going to do a mod 2 on them. And so we need the index, we need to know what the index is for these cards that came in so we can do a mod 2 on them. And so in doing that, we're going to use something called a tuple 2 in the context of Project Reactor. So anyway, that's index. So once we've indexed them, all the cards, we're going to take 9 of them. And then we're going to filter, only allowing the ones that are mod 2. So the 0th card, the 2nd card, the 4th card, the 6th card. And then we're going to map, and I'll describe this in a minute. We're going to map to get the actual card out of the tuple, and then we're going to sort them. Okay, so the index operator, what it does is that takes a flux of elements, and it maps it to a tuple 2. So it's just a tuple, it's a structure that has 2 attributes in it. One is the index, and that's the index of its position in the stream. So we have 0, 1, and 2. And then the second attribute, property, whatever, of the tuple is the original element, the element that we got. So here we've got this tuple is going to have 0 and the element. It's going to have a 1 and the element, 2, and whatever element this was. So it returns, the index operator returns a flux of tuple 2s, a flux of these. And this tuple 2 has a long, which is the index value, and a T, a type, which in our case is a type of card. So that's the index. So then another way of viewing that index is in a table here. So we'll just take the first 4 cards. So these are the index values, and then these are the tuples, long and a card. Here's the value coming in. That's the actual card. And if you want to see the tuple documentation, you can just click this and see the tuple API. And the other thing that we haven't seen, we've seen these other things, right? Take and filter and map. But the other thing we haven't seen is sort. And sort is, it takes a comparator, it takes a flux, and it's going to sort the flux. But until the flux completes, we can't sort it because we don't know all the elements that are in the flux. So that's why we see the completion here before the flux, the elements are output on the flux that's produced. So here we've got the input, and here we've sorted it. And so then here's pictorially what's going on. We're going to take 10 cards. Get rid of that. Let's see. Sorry. We're going to take 10 cards, and then we're going to process them. I've got to get rid of this here. Okay. And so you'll see how they're processed. Going to run through the index. For example, whoops. Okay. So the first card got processed by the index, got turned into a tuple 2. And then, so what do you think is going to happen next? That tuple 2, I know I'm out of time. The tuple 2 is going to go down to the take. Take gets decremented. Right? Then it's going to get filtered. Is it going to pass through the filter? Yes or no? Yes, because it's a mod 2. 0 mod 2 is past that filter. And then we're going to map it to the original element, which is get T2. That just takes the tuple and gets the original element. And then we're not going to sort yet because we can't sort it until the sort. Remember, it needs to have all its elements before it can actually do the sort, because we need to know what to sort. So very quickly go through here. And we see that the 5 got through, the tuples got through, and then go down to the sort, and it completes. And so that's a good time to stop. And you have a choice of MVC or WebFlux or both. You can play. And then these are the things we've covered. And thank you very much for your attention and participation.